look at what we call small angle approximations for sine, cosine and tangent. So small angle approx. Note, to begin this, we are considering theta in radians, and this makes sense because we get more small angles. If we consider in degrees for a start, these don't hold for one, but they, more importantly, they just logically small angles. I mean, the only small angles you get in degrees is, you know, less than 1, and that's barely a spectrum of angles to consider, so the small angle approximations would be useless anyway. Whereas with radians, a lot of the angles are quite small, so these approximations can be quite good often, and they are. That for small theta in radians, sine theta is approximately equal to theta. Cos theta is approximately equal to 1 minus theta squared over 2, and tan theta is approximately equal to theta. Okay, and if we think about y, especially for we'll just use sine as the example. You haven't seen this yet in A-level maths, but I've got a video on it, and if not, I'll just give you all the information you need for now. But sine theta can be, and cos theta, you can do the same on a tan, can be written out as a series. Okay, so sine theta is theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, and you see the pattern here. Okay, it's just oscillating sine, and it's all the odd powers and odd factorials. But here, if we first notice that these denominators are getting quite big, okay, and quite big quickly. So okay, this is only 6 or whatever, but this is 120, and I can't even bother to work that out, but large, right? It's a big number. They're getting bigger and bigger and bigger, and if theta is small, you know, less than 1, say, even, these powers are getting small, these numerators are getting very small. So if the numerator is small and the denominator is big, I mean, these whole terms essentially just go to 0. That's why this approximation is better and better for smaller and smaller angles of theta, but it's still a pretty good approximation for all small angles. And you can do something similar, because if you look at the expansion, after this term, the next power of theta is to the power of 4, and that's just tiny, and yeah, and we'd have over 4 factorial, which is 24. Okay, so all these terms just sort of disappear, so that's where you get this expansion from. Next thing on the specification, just to kill 2 birds with 1 stone in this video, is knowing some specific values of sine and cos at various values of theta, so in radians. So theta is in radians here. So of course at 0 we still have sine 0 is 0, cos 0 is 1. Okay, then we have pi by 6, and pi by 6 is equivalent to, well, pi is 180, so pi by 6 is 30 degrees. So this is 1/2, and this is root 3 over 2. Next up, we've got pi by 4, and this is 45 degrees. So sine 45 is equal to cos 45, because sine of theta is equal to cos of 90 minus theta. Okay, so at 45 those two things are equal, and this is equal to root 2 over 2, and that's root 2 over 2. Okay. Next up, we've got pi by 3, and this is 60 degrees. And if we use our 90 minus theta rule, well, this is just going to have to be the opposite of this column. So we're going to get root 3 over 2, because sine 60 degrees is equal to cos 30 degrees. And here we get a half by similar logic. And then finally, not finally, pi over 2. Okay, this is 90 degrees, so 1, 0, and pi 0, minus 1. Okay. So those are nice to remember, but that's all we're really going to cover in this video. We'll be looking more at trigonometry in radians in the upcoming videos. For now, that's it. If you've got any questions, let me know down in the comments below, and I'll try my best to clarify any queries. That's it. If you did enjoy, please like and subscribe, and I hope to see you in the next one.